Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through subgroups. So a subgroup is a subset of a group that is itself a group. What that means is we take a group, we take some of its elements, and those elements form their own little group. That's what a subgroup is. So how do we determine if a subset, if a set of some of the elements of a group is a subgroup? Well, it needs to satisfy three axioms. So firstly, the subset we're talking about needs to be closed. It needs to have the identity element as part of it, and also needs to have inverses. Remember though, when we're talking about groups, a set forms a group under a particular operation. Could be addition, multiplication, composition of functions, or whatever. So when we're talking about these three axioms, they need to be true with respect to the same operation that the group was formed under. So if the group is a group under addition, we're talking about the subset being closed under addition. It contains the additive identity and it contains additive inverses. Of course, if the original group was a group under multiplication, we'd be talking about closure under multiplication containing the multiplicative identity and multiplicative inverses. So it needs to be with respect to the operation the group was formed under. So these three axioms should not look foreign to you. In fact, they're three axioms we learned about for something to form a group. What is different though between this and a normal group is, remember, there were four group axioms. There's one missing from this list of three, and that is associativity. So I don't need to check that for a subgroup, because if a group is formed under an operation, say addition, that means that every element of that group is associative under that operation. So that means that any subset of that group will also be associative. So the associative law is induced on any subset as it is. So I don't need to check that. I only need to check the other three, because that's not induced by the group. Of course, if I take any subset of a group, it may not be closed even though the original group is closed. It may not have an identity as part of this subset, even though the original group had an identity. It may not have inverses in this subset, even though the original group had inverses. But it will definitely be associative under the operation the group was formed under. That's why I don't need to check associativity. So to understand better what a subgroup looks like, let's go ahead and look at a group that we know and what some of its subgroups will be. So let's look at the group of integers under addition. So the set of integers forms a group under addition. We know that. In fact, this is a subgroup of the rational numbers under addition, which is itself a subgroup of the real numbers under addition. But let's treat our group as this, the integers under addition, and let's look at subgroups of this group. So it turns out that a group will have at least two subgroups, itself and what we call the trivial subgroup. So the reason that something is its own subgroup, or more precisely, a group is its own subgroup, is because any group is a subset or equal to itself. So the group of integers under addition is also its own subgroup. So that's one subgroup of it. The trivial subgroup is just the group that contains the identity. So in this case, because we're talking under addition, we're talking about the group that just contains 0, because 0 is the additive identity. So 0 is its own inverse, and if you add 0 to itself, you get 0. So this actually satisfies all three of the axioms up here. So it's kind of like how for any integer, it has at least two factors, itself and 1. So this trivial subgroup is kind of like 1. But we're normally not interested in those factors when we're factorizing an integer, just like we're not really interested in these subgroups when we're looking for subgroups. So these two are sort of called improper subgroups. We're looking at proper subgroups, subgroups other than the obvious ones. The trivial subgroup, which just contains the identity, and the group itself. I just want to point out that if we were talking about a group under multiplication, this trivial subgroup would just contain the element 1. But because we're talking addition and the additive identity is 0, this subgroup contains 0. Let's now construct a proper subgroup of the additive group of integers. So I'll call it S, and it'll be a set with some integers in it. Now, because a subgroup must contain the identity, and this is a subgroup under addition, 0 must be in this subgroup. If it's a subgroup under addition, it must contain 0. But I want it to be a proper subgroup, so I need it to have an element different from 0. So let's call that n. So n is not equal to 0. Now, if n is in my subgroup, because each element's inverse needs to be in this set, that means negative n will also be in this subgroup. So that will satisfy the second and third axioms, but not the first. If I just have minus n, 0, and n, it is not closed, because if I say add n to itself, I get 2n. n plus n is 2n, so I need to include 2n in the group as well. Similarly, minus n plus minus n is minus 2n, so I need to include that. But if I include 2n, I need to include 3n, because n plus 2n is 3n. And similarly, I would need to include minus 3n as well, and so on. So what we have here, this subgroup will be infinite, just like the original group. So what we have are positive and negative multiples of n. So that is what any proper subgroup of the additive group of integers will look like. Positive and negative multiples of a given integer. So for example, I could have the subgroup that is all the negative and positive multiples of 3. So it would have no lowest element, and it would keep going. Minus 3, 0, 3, 6. It would keep going forever. It needs to be infinite. Otherwise, it won't satisfy the closure axioms. So any set like this will be a subgroup of the additive group of integers. It is a subset of the integers that is also a group. And any integer will do. Positive and negative multiples of 2, positive, negative multiples of 23, they will form a subgroup of the additive group of integers. Now let's look at an example of subgroups of a finite group. So I want to introduce you to another type of group, the cyclic group. So it has elements that are powers of some pronumeral, like C, I'm going to call it, that form a group under multiplication. So the cyclic group with 6 elements, the cyclic group of order 6 has these 6 elements, 1c, c squared, all the way up to c to the power of 5. So how would this possibly be a group? Well, it would only be a group if I have something like c to the power of 6 is equal to 1. That's the only way I can make sure inverses are in the group. And this would need to follow the normal index law that c to the k multiplied by c to the power of l, keep the same base and add the powers, okay? So this would form a group given these two rules here. It forms a group under multiplication. And you can check the axioms if you don't believe me, but we're going to look at subgroups of this. So this is a finite group, unlike the additive group of integers, because there's only 6 elements. There's a limited number of elements. So, of course, just like the additive group of integers, this will have at least 2 subgroups, itself and the trivial subgroup. In this case, the trivial subgroup would be the subgroup containing just one. So these will be subgroups, but again, they're not proper subgroups. So let's go ahead and find some proper subgroups. So I've written 3 sets here, and we will go through and see which, if any, form subgroups. So firstly, notice that all 3 of them contain the multiplicative identity because this was a group under multiplication. So that part is fine. So let's look at now whether inverses are in the group. So first group, 1 and c to the power of 3. Well, because c to the power of 6 equals 1, this means c3 times c to the power of 3 is equal to c to the power of 6, which is equal to 1. So c to the power of 3 is its own inverse. Of course, 1 is its own inverse. It always is. So this group does contain inverses. Let's look at the second one. Same thing. C to the power of 2 and c to the power of 4 are inverses. So they multiply to give c to the power of 6, which is 1. So they are each other's inverse. Of course, here multiplication is commutative because we're using our normal index laws here. So each element in this second set has an inverse. And same in the third one. Each element has an inverse. C and c to the power of 5 are inverses because they multiply it to 1. So that's great. So far we know that all 3 of these sets have the identity and inverses. The last thing we need to check is if they're closed. So the first one is clearly closed. That's because c cubed times 1 is c cubed, which is in the group, and c cubed times by itself is equal to 1, which is in the group. So this one is a subgroup. It satisfies all 3 axioms. So let's look at the second set to see if it's closed. So this is a group with a small number of elements. This set has only 3 elements. So to see whether it's closed, rather than trying to do some proof, what we might do, we might rub this out for space and we'll look at a product table. So we're going to go and fill in this table. So this is through multiplication, and here multiplication is commutative because we're just following the normal index law. So 1 times 1 is 1, 1 times c squared is c squared, and so on. So c squared times c squared gives you c to the power of 4. C squared times c to the power of 4 gives you 1, as I explained earlier. So that one will be 1 as well. So c to the power of 4 times c to the power of 4, keep the same base and add the powers. But because c to the power of 6 is 1, this will just be 1 times c squared, which is c squared. So we can see that these 3 elements are closed under multiplication because any of the products are members of this set. So this one here is a subgroup as well. It's satisfied inverses and identity. We showed that before. Now we've shown that it's also closed. So the first 2 both constitute subgroups. The third one, however, does not constitute a subgroup. As we said before, it does have inverses, it does have the identity, but the reason it is not a subgroup is it is not closed under multiplication. Because if I times c by itself, I get c squared, which is not a member of the set. Similarly, c to the power of 5 times c to the power of 5 would be c to the power of 10, but that's c to the power of 6 times c to the power of 4, because c to the power of 6, remember, was defined as 1. It'll just be 1 times c to the power of 4, which is not a member of this set. So it is not closed under multiplication. So I'm hoping you see for this, because we're going to come back to it in a couple lessons time, there is a lot of similarity and a lot of similar structures between this group and the integers modulo 6, but we will come back to that. So far, we've just looked at subgroups, subset of a group that satisfies the 3 axioms of closure, identity, and inverses, and went through a few examples. I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.